Okay, so our first speaker is Shosei Anegawa, and he will talk about Bootstrap meta learning. Go ahead, Shosei.
Okay, so I'm going to be talking about the paper Bootstrapped meta learning, as we said. So first, just a little bit of background on what meta learning is. So whenever we apply machine learning to a problem, there's always the question of what algorithm do we use and how do we tune the hyperparameters? And the idea with meta learning is let's use another machine learning algorithm to do that for us, to tune those parameters for us and decide what algorithm we should use for us. In this case, we're going to be focusing specifically on online meta learning, which is a form of meta learning that improves the algorithm, in this case, by changing hyperparameters as the algorithm is running. So for example, for a neural network, that would be something like the learning rate. It would change that as it's running to make the algorithm perform better. And a more technical way of saying that would be we're trying to treat the hyperparameters of the update rule of the neural network as a learning problem. And I'll go more into detail with that later. But first, I want to introduce
So Shosei, there should also be meta learning, right? So if you have a learning algorithm to learn a hyperparameter, there is an architecture and hyperparameters used for that. And so then you would want to learn that as well, yes?
Yeah, I mean, there is at least one hyperparameter for meta learning. So you would, that wouldn't be the worst thing
but
ever.
there has to be more, right? So hyperparameter, like, learning rate, there is still architecture. And so this could be meta learning and meta learning and so forth, but okay. Sorry.
Okay. So first, I'm just going to introduce the notation because some of it is a little bit unintuitive. So in this case, f is going to be the expected loss function of the learner. That's not the meta learner, but the learner underneath it who's trying to optimize this loss function. And in this case, we're using x to denote the learner's parameters instead of w because the meta learner's parameters are a separate thing, and the meta learner is not learning the learner's parameters. It's just that its parameters have an effect on it, so it can be kind of thought of as the state of the meta learner. These are the learner's parameters. And then W is the meta learner's parameters, which can be a lot of different things, but I'll give some examples later. H is the learning state, which is just kind of a catch-all term for anything that we need to compute an update rule that isn't a parameter. And again, I'll give an example for this later. And then lastly, there is phi, which maps x cross h cross w back to x, which is just the update rule. It just returns a second term in stochastic gradient descent, for example. And right below, there's just an example of a parameter update x superscript 1. That just means the update rule is applied one time, is equal to the old parameters x plus whatever the update rule is. And that update rule ends up being the meta learner's objective function. So as an example, quick example for stochastic gradient descent, it's just the update rule that we all know, which is x minus the learning rate times the gradient of f of x, where in this case, h, the learning state, would just be the gradient of f of x because it's not a parameter, but it's necessary to compute the rule. And then the meta learner's parameters would just be one thing, the real number alpha, the learning rate. So one last thing before we go into the Bootstrap metagradient, I just want to talk about the standard metagradient, which is how it's been done in the past. And it's kind of done exactly how you'd think it's done. This W here is different from the X back here. This X is computing the learner's parameters. This W is updating the meta learner's parameters. In this case, well, for stochastic gradient descent, that would be the learning rate. And XK, again, denotes K applications of the update rule. And so all you're doing is you're subtracting some beta, which is another learning rate like term for the meta learner, times the gradient on W of XK. So one thing to note about this is that there is no actual assumption on what W is aside from differentiability on it. So this could be a recurrent neural network. This could be whatever you want. And it's also used for reinforcement learning, as I'll talk about later in the examples. The thing with this is that it raises two issues. The first is called myopia. And this stems from the fact that to compute this update rule, to update the parameters of the meta learner, update W, we're only looking at K steps, which is not a very large window in the grand scheme of training. And so this ends up only optimizing for those K steps, which doesn't necessarily help training in the long run. And of course, you could increase the window size, increase K, but that just increases computational cost, and it's not necessarily even going to be helpful in the long term. The second problem is curvature. So since the update rule, the W prime, which is the new meta learners parameters, is defined directly in terms of the learner's loss function, which is f. There can be problems if f is ill-conditioned, and it sometimes is, where small changes early in training can cause much larger changes later, and it's difficult for the meta learner to catch on to those and try and decide where it should push the learner's parameters, how it should change the update rule to account for that. And people have corrected for this in a number of different ways. I think the most common way that the paper mentioned is that they would just use, for example, like the Atom optimizer on the underlying learner to try and smooth out the whole loss function. But it's not, they're not super ideal. And so the two changes.
Shosei, can I like I'm trying to better understand this, so
Okay.
Sorry, I'll keep interrupting you. So k is the number of it's like a mini batch size for the regular learning, right? So how many steps do you have to go through to before you actually take a gradient descent? So that problem exists in the regular learning. It's nothing new here. By changing your mini batch size, you change how your algorithm performs. So k is your hyperparameter for this meta learning, and so there's
so k is one of the hyperparameters. Later there'll be another hyperparameter that gets introduced, and so is beta learning rate.
And then the curvature is also this is known from the regular learning as well, right? So you can have the small curvature can have small impact or can have large impact depending on what the gradients you have. We can have a problem of flat directions that there is no change in certain directions, should not be even training there. And so those are not, so I guess my point here is that those problems are not unique for meta learning. They're just, general things that are present in all learning tasks.
Yeah, so I guess that could be interesting trying to apply this to normal learning.
Okay.
But yeah, so anyways, to address those two problems, the paper introduces two additional things. The first is a target bootstrap, and the second is a matching function. And the idea with the target bootstrap is that it looks in the future of learning. It tries to see where we would have gone after the k steps if we had continued training, and then you adjust the meta learner's parameters based on this to try and get there faster. I'll go more into detail on this later. And then also there's the matching function, which is just a function that measures distance, some function that measures distance to the bootstrap target. And the idea with this is it's no longer going to be defined directly in terms of the learner's objective, so we can kind of control the curvature and make a smoother, easier to learn function for ourselves. So the first thing is target bootstrap, which I'm going to denote as x tilde from here on. And what it does is it estimates the new parameters after applying phi, the update rule, for another L-1 steps. It says if we had kept learning for L-1 steps, where would we have been? And the issue with just naively doing this is that the bootstrap won't necessarily be making the learner better. It could be actively making it worse. And so the idea is the paper adds on an additional step, which goes in a direction that we know is correct. So you'd take a step down the gradient of f in order to make sure that like the bootstrap is going in the right direction. So it would nudge it in the correct direction. So the general update rule would look something like x tilde is x to the k plus x with k plus l minus 1 update steps applied, minus some learning rate term alpha times the gradient, times one step in the gradient direction. And the idea again is that it mitigates the close-sightedness by looking forward more.
Well, okay, but you're looking forward more, still going along the gradient, right? So if you really want to look more, then there's, for example, Newtonian method. You can approximate your function not as only a slope, having a second derivative, and then you can calculate what is the minimum and then take a step there. So I guess my question is, what does this taking more steps mean? Is it just equivalent to increasing alpha, the learning rate, or?
So the additional steps, you don't actually take them physically. You define a different function that that sort of models taking them, and then you would try and push the xk, the k update rules, towards that new location. I have more example functions later. I'm not sure if it'll help.
I mean,
but
you're not changing f, right? You're not changing the loss function.
No, the loss function is staying the same.
Okay, so then Okay, I guess I don't understand what.
Okay. Yeah, we'll see if maybe the later parts make it better.
Mhm.
But then the second part is the matching function, which just measures the difference between the x with k update steps applied, k times the update rule applied to it, and x tilde the bootstrap. So again, this allows for a smoother optimization landscape since it's no longer directly in terms of the learner's objective. And the example that the paper uses is something like KL divergence, because really what we're doing is just comparing two distributions, and that's what that does well. So there's the visualization on the right side over here that shows W being applied k times to x, leading to a new spot. And then there's a dashed line down, which is the bootstrap in this case, where it estimates where it would have been further down, projects it onto the matching space, compares two distributions, and then sends a gradient with respect to W, which is the parameters, back to the first one. And then it gives you sort of the direction of where W is going and W tilde.
Yeah, so it looks like they're actually extrapolating function to include higher and higher terms in the expansion. So instead of just doing like linear expansion where you would go, in order to see all this curvature, going around and turning, you include higher order terms in the expanding of f. Because how else can you figure out that this trajectory has to make a turn? Only if you keep expanding f to higher and higher orders. Linear just gives you gradient descent, and then higher orders give you more. So I guess that may be what's happening here. You just take more derivatives of f and then use that to determine which direction you should actually be going.
Yeah. The example,
how else, right? So you have a function. I mean, again, it has nothing to do with this particular meta learning task. You have a function, you're trying to minimize it. You can take a derivative, but that's gradient descent. Or you can take its second derivative, you can take third derivative, fourth derivative. The more derivatives you take, the further away you can extrapolate your function, and better you can approximate the minimum, the direction in which you should go. Okay, yeah, just a general statement, yeah.
Yeah, sure. I don't know if the target bootstrap function that they provide, like the example function they provided, had second derivatives in it, but we can look at that when we get there.
Right.
So anyways, together they make this equation W tilde, which just looks like a gradient descent update with the gradient on W with of the matching function. So just to bring up an example of this, the standard meta gradient all the way from back here is just a specific case example of this of the bootstrap meta gradient, with x tilde being equal to k steps applied to it minus half of the derivative, the gradient, sorry, on xk, with the matching function being the difference, the squared L2 norm. And if you just stick in the target bootstrap into the x tilde, you can see that it works out to gradient on W, which yields the same exact equation. And D right there is just the Jacobian of the update rule being applied k times. And then they also set out some proofs for performance guarantees, which I'm kind of going to skip over because they were really long. But basically, they showed that both the normal meta learner and the bootstrap meta learner were guaranteed to have improvement by just doing Taylor series expansions on the equations and bounding the terms above. And then they showed that for a specific target bootstrap function, this one right here, with D again being the Jacobian, that the bootstrap meta learner performed better than the normal meta learner. Sorry, at least as good as. Yeah, but again, I'm kind of going to gloss over this because they were really long. And now just onto some of the experiments that they did. They mostly used reinforcement learning for the experiments because RL kind of tends to have very impactful parameters that for optimal performance need to be tuned during training a lot. So in this case, their first experiment was with just a tabular grid world infinite horizon problem, so it would never end, with two items in it that whenever the agent picked up an item, another item would spawn somewhere else. And one of the items would yield a +1 reward and another -1. And the important part about this is that the rewards would flip every 100,000 or so steps. And the idea with this is that every 100,000 steps, the agent doesn't have a memory, so it doesn't know that it's flipping at every 100,000 steps. So it would have to learn have to know to change its parameters, and the most important one here being the entropy rate, or more commonly referred to as like epsilon in an epsilon greedy policy, which measures how much an agent explores. And the idea would be it needs to start exploring a lot more. It needs to realize it's doing that and then start exploring a lot more at the 100,000 step intervals, which you can see it doing in the graph on the right, which I thought was really cool, how the entropy rate jumps up at 100,000, 200,000, 300,000, and same with the normal metagradient, but just not as much. And on the left, there's just a graph example of performance, and you can see the metagradients tends to do better for smaller bootstraps. When it gets too high, it sort of performs worse than the normal metagradients, but they are more consistent in general. And then lastly, the other experiment they did was in the Atari ALE, where the idea here is that it's just a more complex problem, and they compared the Bootstrap metagradient to another state-of-the-art reinforcement learning method called StackX, which is also which turns out to also be a meta learning agent. And so it's easy to compare because they just changed the meta objective and ended up having Bootstrap metagradient perform better. Yeah, that's what I had for that. Thank you for listening. Are there any questions? I don't know if you want to talk about the.
No, you can. Are there any questions, comments? Okay, yes. Go ahead, George.
So I've been trying to understand what bootstrapping means in this context. Is this called bootstrap because it uses the same data to get a new estimate?
Yeah, I think so. So basically, the target bootstrap function, this is like the example that they provided and they used in the experiment. It just estimates it based on some of the Jacobians and the gradient, which kind of simplifies into the gradient of W. So it's just an estimate based on the current learning that we've been doing.
Okay, so no new data is necessarily added. It just uses some of the old ones.
Yeah,
okay, that makes sense. Thanks.
No, but I mean, again, I'm also confused here. So if you do use the previous data, or I guess, then effectively, I think you are calculating just the higher and higher derivatives of f, right? So you calculated your first derivative on this time step of f, first derivative on the previous time step before that. So basically, you have all those derivatives, and you have changes on those derivatives. So really, you can better approximate what f function is, and then you can use it to, if you have second derivative with Newtonian method, you can use it to estimate where the function minima is. And so I think that's the idea. That I mean, I'm viewing this k as high and higher orders of Taylor series expansion that allow us to estimate. I think guess what's missing here, maybe mathematical formula showing how all those previous steps can be used to find this x tilde. That's what I don't see. So they write some x tilde, but how do I actually calculate that? Because x tilde is where you want to go, right?
Yeah.
Okay. So then I have f prime in the k previous steps, and so now, or f in the k previous steps, it doesn't matter. And that's kind of probing function at different points. And if you probe function at different points, the more points, the higher derivatives you learn. And so then you have to use it to calculate your x tilde. So I just don't see here the formula for x tilde.
Yeah, this was
there is this formula.
I didn't. Yeah,
there is this formula, but it's just one k there. So I would think that all k's are different steps, right? K
different applications of the update rule.
Right. So I guess I mean, the point here is that you should use all of those. I think. I mean, maybe I'm wrong with something here, because how else can you estimate better where the minimum of the function is, unless you take higher and higher derivative or estimate the higher derivatives? I just don't see any other way of doing it. But
I
So
see.
maybe the key confusion here is hidden in the K and how the different Ks are used to calculate X tilde. I guess that's
Yeah.
okay.
I think
Go ahead.
I think in the paper they did explicitly say that the gradient does go back through all the Ks. If that.
No, I understand that,
Yeah,
but
okay.
it's a different gradient at different Ks, and so you have like a lot of information when you and then you can kind of somehow have to use all that information to calculate X tilde.
I see.
Maybe they're doing something else, but again, just by taking the derivative of the function, the best you can do is a gradient. By taking second derivative, you can already do something better. You can find what the minimum of the function would be if it was a quadratic function. If you take third derivatives, now you can approximate it as a cubic function and so forth. And so I don't think this is what they do, but this would make sense, at least to me. Other questions?
Going back on the equation that you have right there, what are the d's? Is that derivative?
D is supposed to be the Jacobian of this term right here, xk.
Okay, so it is a derivative of a derivative.
Yeah, there's kind of one term there like that, but then this ends up simplifying just into the gradient with respect to W.
I'm just guessing it is just the change from derivative with respect to X to derivative with respect to W, or maybe.
Yeah.
Okay.
So this is Jacobian from, and what is W? And W is your
W in this case, this is just a notation that's saying that we're applying W and like over here is W tilde. W is the update, the meta learners parameter. So we're applying the meta learners parameter. We're applying the update rule from W to xk times.
So to move in the direction of minimizing the function along the direction of X. Yeah, that's still not making sense either to me. Oh, okay, it doesn't. Maybe it does. So you have a df dx. Yeah, it would be nice to see explicitly what kind of Jacobian that is. But,
yeah. Okay.
Okay. Other questions? All right. Thank you.
Thank you.